So, first of all, thank you for attending class. Class will about harmonic oscillators, and we will try to construct them from the bottom to up to top. Okay. So we will use harmonic oscillators a lot in this lecture. So please try to capture when you see a harmonic oscillator. Okay. We will start with classical harmonic oscillator in, I don't know, classical mechanics. Then we will try to make it into quantum level, and then we will define quantum fields. Okay. And after we define the quantum fields, we will come to decide that we have a background geometry on that quantum fields. So that with those background geometry, we will see that there is some harmonic oscillators inside the theory, and also we will have some conclusions about what is vacuum, what is the relativity perspective of the vacuum, and we will see a lot in those perspectives if I can manage to make it on time. Okay? If I can't, maybe we can proceed next week, no problem, if you like to attend. So then, let me write the motto of this lecture. So this is what it is, basically. The career, okay, of a theoretical physicist. Let me just change my physicist, right, okay, consists of treating harmonic oscillator in ever increasing level of abstraction. Okay? So, this sentence belongs to Sidney Coleman. It's a very important sentence, let's say, because we really try to find something that we can understand. In that case, simple harmonic motion, something that we really understand in the end. And we try to build up models from that understanding, okay? And with that perspective, of course, let me just erase that. With that perspective, we can start with classical harmonic oscillator that we all love to see when we are in the undergraduate, okay? So, 1. Simple harmonic oscillator. Let me write HO for harmonic oscillator, okay? So what is a simple harmonic oscillator? It is anything with, okay, a linear historic potential. Okay. So from that, directly comes to mind is spring potential, right? And the equation of motion for a spring. You know that guy, right? This guy, you know that. So of course, if you try to solve this differential equation, if you know differential equations, I hope you do, you will find this kind of solution with respect to, of course, the initial conditions and all. And of course, we just divide by m. This is 0, so we know the frequency as what it is, square root of k over m. Okay? We try to define it as square of something to solve this equation easier. So we know the frequency of this oscillation. Okay? We will use that frequency a lot. So let me just try to play with this solution a bit. You know, we can write cosines in terms of e to the i's, right? You know that. So maybe I just write them again as another solution that will solve this equation again. right? Like this. This is again another solution. This will correspond somewhat like plane wave solutions, right? And then you know that because of the potential here, the Hamiltonian that will come from this theory, let's say, theory of harmonic oscillators, will equal to the energy of the harmonic oscillators because of the potential term. Okay? So you know that also. How can I find the energy from the equation of motion? You know that maybe from classical mechanics. There's a trick. It's not actually a trick, but it looks like a trick. So what happens is basic. We try to multiply this equation by the velocity, and then we take the total derivative of that velocity, beat the velocity term, and then we will find the kinetic energy and the potential energy, right? You know that. So x dot parentheses, we will have what? D square x over dt square plus k over m, again the frequency thing, and this will equal to 0. Since the equation equal to 0, when I did multiply with x dot, I have nothing wrong with that, okay? And then if I take the derivative out and do all the manipulations, I will find this guy. Okay, I will find this guy. Let me just try to write it in a way that we can understand further on. Okay, this dude, and again, this will equal to 0. So, simple question is this: when we try to work on these harmonic oscillators, after with that potential, we can see that if this is energy, you know that this is energy, there is time change and it's squared, and there's something like a potential in here, right? And its derivative is 0. That means if this is energy, the energy is a constant in time, okay? If it's a constant in time, then it's conserved, right? This is the basic thing that you can understand. So if I call this Hamiltonian, if this is Hamiltonian, then derivative of the Hamiltonian is 0, that means Hamiltonian is conserved. Since the kinetic energy is quadratic and the potential is not depending on anything other than the position, we can say Hamiltonian is conserved, and also Hamiltonian itself is equal to the energy. Okay? That's a simple thing. You know. So, what can we do next? Okay, we now know what is a classical harmonic oscillation, also a simple one. We know that. We can try to write a theory, a quantum theory of these harmonic oscillators, so that maybe we can understand their quantum site, right? How can we do that? We can just try to identify what are the degrees of freedom, right? So we are lucky. Why? Because we have the Hamiltonian. If we manage to write the Hamiltonian, that means that we know the degrees of freedom of the system, right? We know in a way that if we can fully write the Hamiltonian, we know the degrees of freedom. If we can quantize all the degrees of freedoms, then we will have the corresponding quantum theory of the classical theory, okay? So let me just give something. We don't know how to quantize things, okay? We don't know the quantum theory. We don't know that, okay? We are not too small. We don't know intrinsically, okay? We cannot feel the quantum system. We are feeling the effective description of that quantum system, which corresponds to a classical notion. So to understand the quantum system, we try to quantize it. Quantization is not a thing for electron itself. It's a thing for humans to understand how electron behaves, okay? Quantization is a process that is deemed to humans, okay, to us. So quantization is a made-up thing. Everything is quantum. So what we understand is classical site. If we try to quantize the classical site to find the quantum version of it, if that quantum version is correct with the experiments and all, we can say that, okay, this is the corresponding quantum system. So the best way to quantize something is to know its degrees of freedom. If we know its degrees of freedom, we can quantize those freedoms, the physical degrees of freedoms, so that we can find the corresponding quantum system. To come here to that, I will not show it to you, but I want to give the word, okay? There is something called geometric quantization, okay? Please know it. is one of the quantization methods that is heavily used by mathematicians, okay? So the geometric quantization know the word, so please Google at one time. Please Google geometric quantization of simple harmonic oscillator and try to understand what is the geometric notion behind it, okay? You will see something called omega, okay? It will look like this. It will look like this. You will see something called Kepler polarization, okay? So you will see something called holomorphic functions and all, okay? Please try to understand this simple quantization procedure from a higher geometric perspective. I'm not going to talk about this, but I want you to self-study it, okay? That's a good thing to know. Okay, a good procedure to know. So let me just raise it and try to directly write the quantization of the system. Okay? Try to directly write it. And then we can go with that, okay? So, what can we do? We know the physical degrees of freedom, its position. We can directly quantize that position, right? And of course, its momentum. We can directly quantize that momentum. The reason that we can directly quantize it, because the geometric quantization structure is trivial. We can directly quantize it. This triviality allows us to do this easy. Okay, we can just say, okay, this was position in classical system. Now this is an operator in a quantum mechanics. This is again the same because of the triviality of the geometric quantization. Okay, so okay, now if we say that these are now operators acting on the Hilbert space, we can just directly know, maybe, okay, they're commutators, right? We can say it's I, okay? If it's ij, it's gamma ij, we have delta ij, we have, and all. And then you can directly write, if you took quantum 300, you know this guy, right? It's the Hamiltonian in terms of the ladder operators. What are the ladder operators then? We can directly write it. M omega over 2, right? X plus IP over M omega. And that's the second thing. So its dagger will correspond to a minus sign in here because of the I. You know that? Okay then. We now know the quantum version of this Hamiltonian operator. Now it's an operator. And now we know how to construct the states in the Hilbert space, just looking at the laddering of the vacuum state. If we can ladder the vacuum state up, we can find the eigenvalues corresponding to this Hamiltonian, which corresponds to energy eigenvalues, right? Then we have the old quantum system. That's that easy, okay? But this thing is somewhat important. You know, this ladders down the state. This ladders up the state. If you act something consecutively, you won't change the laddering. Ladder up and ladder down and ladder up, right? So this will correspond to the number operator. With that, you will know the state in which particle number if you act on something, okay? So what I mean is this. With the number operator you see in here, if you act on a state, right? The state will give you the number n from this equation, and it will give you the same state. Other than acting with, let's say, ladder up. I will say ladder up now, because we are working on quantum mechanics, but when we come to quantum field theory, I will say this is something of a creation operator, okay, creation. You will see that creation and annihilation, we say that there's a reason for that, okay, you will see in a bit. This is now just ladder operator. You ladder up or ladder down, okay? Now we try to ladder up the quantum system, that's it. Let's ladder up this harmonic oscillator, square root of n plus 1, you know, n plus 1. You can go up to top and act on the top ladder and find 0, or you can go down, find the vacuum state, and act on the ladder down, then you can find 0 again, okay? That's all the complete set of eigenstates that you can find so that you can find a good Hilbert space from that. And in the end, you have the quantum mechanics. Okay? That's the quantum mechanics in an easy way. Okay? I know it's a hard course maybe sometimes, but in my perspective, this is all it is. Okay? Then, what can you do? You can write an equation if this ladder operator evolves with time. Right? You can write an equation. We will use this equation again in quantum field theory when I start that. But this corresponds, this Heisenberg equation, okay? It means that, let me just look at this equation and try to understand what it means. Okay, what it means. It's really simple. It says this. If I try to commute something with the Hamiltonian, something, I don't care what it is, something with the Hamiltonian, this will correspond a time evolution. So Hamiltonian is something like a time evolution operator in that sense, okay? In that sense. So I can find any operator in here and its time derivative will correspond to that, okay? In that sense, in that sense. So if I try to just, I know Hamiltonian in terms of the lettering, I can just place it in here, do all this work, and in the end, I can find the result of this commutator. Let me just slightly show it to you, slightly, not losing much time on it, because we have a lot of things to do. I know that you might know these things. I don't want to bore you again in that sense, but let me just write it very, very quickly. Okay? Okay. And then A1, 2. Okay, this guy. You know, A commutator will be 0. A, this constant, again 0. And in the end, A dagger equal to 1. Lettering operators, right? Not commuting with each other. This equal to 1, omega A we have. Then the derivative of A equals to omega A. What was the omega? Frequency, right? So from here, let me just write it very fast. dA, if I took this A down and dt up, right? And what it means, dA over A will correspond minus I omega dt. First order, simple equation, differential equation. Solve it, too easy, okay? If you solve it without any problems, this will correspond, the ladder operator with the time evolution, right, is equal to the initial data, this is 0, the initial data of the lettering, time independent portion, times the minus I omega t. So you evolve the time independent portion and it corresponds to time dependent lettering. Okay? With these, you can now solve the time dependent, I don't know, Schrödinger equation and all. You now have the quantum system, all of it, for the harmonic oscillator. If you try to expand these states, you will find, it depends on the quantization, but for the quantization our choice, it will correspond Hermite functions, because we have the harmonic oscillator. Hermite functions will correspond its eigenfunctions and their eigenvalues. You know the guy. You can say it on top of your head. Why? Omega is a constant. This is number operator. What the number is comes to that. 1 over 2 is a constant. Then omega n plus 1 over 2 will correspond their eigenvalues. Okay? That's it. So now we did something. We started simple harmonic oscillator for classical mechanics. We come to this quantization. We try to quantize it by just simply stating that the classical position now is an operator acting on the wave function, and the momentum now is an operator acting on the wave function. We just say that, define the commutation, define the Hamiltonian by looking at this guy. In terms of the lettering, let me just write it like this. In terms of the lettering, just letter them all, and find the corresponding quantum system. Okay? Now we will do the same thing. The same thing in a more mathematically involved setting. Okay, excuse me. Okay. In a more mathematically involved setting. So we, unfortunately, this construction is not enough to understand the building blocks of the universe. If you watched, I don't know, if you watch David Tone's lectures on building blocks of the universe, he states that we need fields, okay? Then we will define fields. But even if you don't know what a field is, you already used it because you are physics students, right? You know what an electric field is. It's a field. It's a field. At every point we have a vector. I don't know. Temperature is a field. At every point we have a corresponding temperature, right? Now in this room there's a temperature field. It's a scalar field. At every point you have a temperature, right? That's that easy. But it will be getting more and more involved if you try to do the calculations, especially if you come to the curved space-time. In the curved space-time, things get crazy, and doing them, solving them, are becoming impossible daily. Okay? So, let me just then go on with that. So, from now on, I will use these two books, okay? Just know the books. So, Matthew Schwartz, let me just write Schwartz only. Schwartz, QFT, quantum field theory, and standard model, and Mukhanov, Intro to Quantum Effects in Gravity. Okay, these two books. So from those books, I will try to pick the simplest things possible so that you can just walk with me. I want you to walk with me in the process and understand what I'm trying to say, if I can explain that in a good way. Okay? Anyway, I just raised them. You can ask me anytime. So, let's start with classical field theory. Oh, Siri opened up. Okay. Classical field theory. So, the classical field theory, as I said, we don't know the direct quantization of a system. We don't know. We can start with the classical field theory, then try to quantize it. Okay? Let's do that. But first, let me write what is a classical field theory. Classical field theory, okay, is a mechanical, okay, system with continuous set of degrees of freedom. If it has a continuous set of degrees of freedom, we need to quantize all of them, right? Because we need to know all degrees of freedom. So, let me give an example, okay? Density of a fluid, let's say, density of a fluid, it's a field, classical field. Electric field, at this Maxwellian way, it's a classical field, okay? It's an observable also, in that sense. So, also we can see classical field theory in a different way. Classical field theory is the tree-level, please check this word, tree-level, okay? Not tree, it means arch, okay? Tree-level, tree-level processes of QFT okay, which are the leading order in expansion corresponds to classical solutions. Okay? What I mean is h bar goes to zero limit. So we can also see classical field theory and just admit that that's wrong. That's classical field theory, that's wrong. It's just an approximation of the real quantum system which corresponds to classical solution that we know in our daily life. Okay? We can also see it like that. So let me just give it. So how can we define field theories? Field theories, of course, field theories are defined with Hamiltonian or Lagrangian now densities. Okay? Hamiltonian and Lagrangian densities. We just take the spatial integration of the Hamiltonian and Lagrangian densities to find the Hamiltonian and Lagrangian. Okay? We just work with Hamiltonian and Lagrangian densities, but I will not tell the densities part. I will be lazy and just say Hamiltonian and Lagrangian every time. Okay? But we will work with Hamiltonian and Lagrangian densities. If you want to find the Hamiltonian, you have to take the spatial integral of the Hamiltonian density, or for the Lagrangian is the same. Okay? Now, you know, if you try to find Hamiltonian density functional, okay, which depends on fields, okay, which depends on fields. Let's say the scalar field phi, and let's say it's momentum conjugate. It's like, let me just give you a hint, it's like position and momentum, right? Position for the scalar field, momentum for the pi. It's momentum conjugate, okay? It's the same thing, in a sense, if you want to try to construct an analogy, and we just use Legendre transformation. If you took classical mechanics, you see this Legendre transformation for energy functions, if we have any third year in here, I don't know. And then, this just defined as it is, okay? Lagrangian density, phi, and phi dot, what I mean phi dot is momentum, is equal to momentum density in terms of phi and phi dot as a function, no, phi minus Hamiltonian. Hamiltonian, phi, and phi dot. So it's just this that. You know this guy. I know that you know this guy because when you try to write Lagrangian, if you take the course, P phi, right? P phi, Px, I'm sorry, minus H is equal to Lagrangian. It's the same thing, but in a field theoretical setting. What I mean by field is an assignment of points so that we can understand all at once in all space-time. Okay, fields. We define fields like electric field. For an electric field, at a point you know the electric field. You find it, right? In the first year. The professor asks you, okay, electric field at point X. Tell me. You just tell it. Why? Because it's a field and you know its value at that point. Same thing. Scalar field. It's like temperature, you think. But it's something else, you will see. It's something else. Okay? Now, what I mean by phi dot is the time derivative of phi, which corresponds to phi dot. I can also define it as momentum. Okay? Momentum field, of course. And also, yeah, okay, it's that it is. So now, let me try to define Lagrangian for the system. Okay? What's the Lagrangian? Lagrangian is 1/2 if I write mx dot square, let's say minus the potential x, you know that Lagrangian, right? But now I will just move up to the field theoretical setting, okay? For the scalar field, too easy, okay? It's just derivative, four-dimensional derivative, okay? I will try to connect it to special relativity, okay? I need that special relativity, okay? Field theory is a way to write quantum mechanics with special relativity. So that means quantum mechanics with field special relativity means field theory. That means quantum field theory. That's easy. Okay, that's it. So phi again, phi. Okay. Then you know this guy minus the potential. That's it. Same thing. Same thing in a field theoretical setting. Okay, same thing. So you write it, you know that it includes time derivatives, right? And positional derivatives as a four-vector setting. Okay, this guy. I can write in d dimensions, it doesn't matter. I can say this is time and this is d dimension. That means d plus one dimension. I don't care, it doesn't matter. But I want to keep in the four-dimensional setting. Okay? This is three-dimensional derivative, what you know as gradient. And this is the time derivative. That's it. I just write them in a one way, okay? While conserving the Minkowski metric in that sense, okay? Special. So, okay, you know we have Lagrangian. We have a way to turn the Lagrangian into Hamiltonian. As you know, we need that Hamiltonian to quantize the system, right? In that sense. So let's find the Hamiltonian then. We can write Lagrangian by expanding this guy, right? What it is easy. It's just 1 over 2. There is 2 times time derivative. I just picked the first one. 2 times time derivative. Minus, because Minkowski metric, okay? Minus in the position, plus in the time. And then minus with the positional derivative and the potential. That's it, okay? Just write phi dot square, okay? And then minus 1 over 2, gradient, as I said, as I promised, phi squared, okay? And then minus, again, the potential. You again know this guy, okay? Now I will use this, use that. Please do it yourselves, okay? From here, you can find the Hamiltonian. It's the same thing in the classical mechanics. You can find Hamiltonian. Hamiltonian is just, okay? Hamiltonian is just this. P squared over 2 plus 1 over 2 gradient squared, okay, as a derivative, plus phi. So, it's cool. Why? Because this guy, it looks like P squared over 2m, something like that, right? Also, this guy is just adding the energy, the kinetic energy plus potential energy. You know that kinetic energy plus potential energy is energy, right? Since the system is somewhat conserved in that sense, Hamiltonian equals the energy for scalar fields. Okay? If you just pick this up, pick this guy up, place it, you will find the same thing. This guy. Okay? It's kinetic energy plus potential energy. That's it. Okay? So now, let me just go on with this. As you can see, Hamiltonian is not a Lorentz invariant factor. It's basically a portion of a bigger Lorentz invariant thing, which is the form momentum. It's the first thing in the form momentum, energy. You know this guy, right? The form momentum is something like this, right? E and P. Same thing, E. So all thing is Lorentz invariant. That means its component is not Lorentz invariant. Hamiltonian is not Lorentz invariant in that sense. Okay? But what is Lorentz invariant? Momentum is Lorentz invariant. Energy momentum tensor is Lorentz invariant. It's also the T00 component of the energy momentum tensor, the Hamiltonian. Same thing. Okay? These two guys, mu, let's say, these two guys are Lorentz invariant vectors and tensors. But Hamiltonian is not Lorentz invariant. Okay, you know that. So now let's identify. Let me just erase this guy and just pick that guy up.
Hocam, can I ask a question?
Of course.
When you say it is not Lorentz invariant,
Yeah.
why do we try to use the Minkowski spacetime if it's not Lorentz invariant?
Minkowski spacetime is Lorentz invariant in a sense.
Yeah.
It's the definition, right?
Yeah.
Definition of the Lorentz invariant in a sense. Metric invariant. That's why spacetime is invariant. But the Hamiltonian that I produce from the scalar fields are not Lorentz invariant. It's just some component of a Lorentz invariant vector. Okay? It's just a component. That's it. But itself is not Lorentz invariant. Lagrangian is Lorentz invariant. This is potential. This is a Lorentz invariant factor in that sense. But Hamiltonian is not. Okay? Okay. So, now let's identify. It's a simple identification from now on. We can just find everything. We just find here, we can find everything. Okay? You know, we can now define the kinetic and the potential terms. Okay? As you see, kinetic term, I can say 1/2 phi dot square. You remember this guy. And I can say the potential energy, let me say potential energy now, but it's kind of wrong to say potential energy from now on, because they are not potential energy, it's like potential term, or better yet, interaction term, we will say, but somewhat same thing. I can just use it, right? Why? Because kinetic energy is the dynamical evolution of a system, a propagation of a system. The dynamical evolution comes from time derivatives. So I can just say this is the kinetic system, kinetic term. Okay? And the potential term is the gradient of the field and the potential itself. It can be. There's an identification from that. Okay? So, in the let me just I believe that this is important, so let me just tell it to you. In the context of QFT, what I mean by quantum field theory, okay? We just replace kinetic energies with kinetic terms, potential energy with potential terms or interaction terms. Interaction terms is better, okay? Because it requires an interaction, potential requires interaction. You just interact with something to have a potential. Kinetic term is just a dynamical propagation, okay? So, first rule is kinetic terms, okay, are bilinear. Bilinear. I mean, they should 2, not 3, 2. Okay? What I mean by this, let's say the kinetic portion of the Lagrangian consists, that means consists, okay? 1/2, I'm just shooting some kinetic terms, okay? You don't have to know it. Just see that there are only just 2 fields. Okay, just 2 fields. Field theoretical setting, of course. So, okay. Let me just write one more. What we need to know is just this. They should be scalar. You see, there's a contraction. They should be scalar. They should be 2 fields. There should be 2 fields with some propagation derivative. It's propagation derivative, okay? And also, they can be 2 different fields. It doesn't matter. Phi 1, phi 2, 2 different fields. Scalar field multiplied by this gauge potential for photon. Doesn't matter. It's the kinetic term. What about interaction terms? Let me just write them too. Lint interaction consists, let me just write on top of my hand, lambda phi cube theory, okay? Anyways, I don't know, the electrons interacting with photons, in that sense, I don't know, let me write the gravitation one. Okay. Alright. These are the expansion, linear expansion metric. This is the gravitational interaction in that sense. Okay. These are the interactions. Just try to understand. If you see a field theoretical setting, if you see two fields with a propagation, you will know that it's kinetic term. If you see more than two fields, 1, 2, 3, 1, 2, 3, 1, 2, 3, it's interaction. Okay? Fields interact, not kinetically, dynamically evolve in that sense. Okay? So, now I know that it feels like, let me just not raise it here, okay? I know that it feels like we just go a lot of way, but we will come back to the harmonic oscillators in a bit, okay? We will find a harmonic oscillator from this setting, okay? And we will see that all the theory is constructed from harmonic oscillators, okay? We will see the harmonic oscillator, just a bit, okay? Let me give you the hint. Let me just erase this guy too. Goodbye gravitational interaction. I just erased you. So, okay. Now, let me just show it to you how it connects to this harmonic oscillator thing and how it connects to special relativity. Okay? So, one can combine harmonic oscillator with Lorentz invariance. Better yet, maybe Poincare invariance, but anyway. Let us define our beautiful D'Alembertian, this guy, the box. You can, if you write in LaTeX, you can write the box. It's just box, okay? But it's just D'Alembertian. You will see, okay? So, let me just try to write this equation. The Lambertian of the field depending on space-time, the Lambertian of it is just this. The 2 times time derivative minus the spatial derivative of the field x equals to 0. Okay? So that's it. What can we do? We just still in the classical field theory. This is classical field. We try to solve this equation. We know that it's a wave-like equation. We can find plane wave solutions. We also were in the classical setting, if you remember classical mechanics. The e to the I minus thing. Okay? So we can just do that. What can you do? You can just write the separation of variables. Okay? Something like it. You remember that guy from 210, I guess. Let me just write the separation of variables in that sense. That will solve this equation. Okay? I just split the time-dependent portion and space-dependent portion and then put it inside the equation. There will be 2 times space derivative, 2 times time derivative. Okay? And then it will correspond to what? This t squared ap t e to the ip dot x, okay, minus, okay, I take derivative of x 1 times, exponential will give what? Ip. 2 times ip again. There is minus sign. I is minus, that means plus. Right? This is just that. I'm sorry, minus. I just said it wrong, I'm sorry. So p dot p apt e to the ipx equal to 0. I'm just trying to solve this equation. Why? Because this was the differential operator. I try to make it as something scalar, p squared. P is, you know, momentum. Okay? So, this will correspond to this equation then. Right? P dot P, okay? APT is equal to 0. So this operator now acts on this guy and finds 0. We come here to them, okay? And then now you can find this plane wave solutions of this phi. Because you know that this will give in the Fourier transform setting, This will give you the plane wave solution. This is a wave, right? I can find the plane wave solution. And it's that easy. Then phi xt, scalar field, depends on space and time, okay, is equal to the plane wave solution of the Fourier transform. Okay, Q. And then apt e to the I p dot x, okay, plus ap complex conjugate t. You see that a's, right? You will see that these are the same a's in quantum mechanics. You will see, not now, when we quantize, not now, okay? A e to the minus I p dot x, this guy. Okay, it's nice to have a time dependence in this creation operator or annihilation operator anyway, but maybe we can just put this time dependence into this guy and write it independent of time. You remember this, right? This AT is equal to, when we solved it for harmonic oscillator, A 0 e to the I minus omega t. You remember this guy, right? We now assume again this, not assume what solution will give that, but we will just put it inside and then gather. You know exponentials, when they multiply, you add them, right? You add them. So we can just write it in terms of four-dimensional setting then. Four-dimensional setting, right? Let me write it then. AP, that means every P, we have this guy. For every wave vector, we have this guy. Okay? AP, e to the I, px, assume these are four-dimensional, plus AP star e to the minus I, px. What I mean by px is easy. P is now omega wave number with momentum, okay? And wave number is just the magnitude of the momentum. You know this guy from the waves classes or anyway. And then the four-dimensional setting, px, what I mean by px is just this. This multiplied by this guy, okay, for 0. What is x0? You know, in 4 dimensions, x is time and x, the first component is time. This is t. You know, right? We just take it from here. Omega t. It's now inside here. I multiplied them, okay? Omega t. Minus, right, px. 3-dimensional portion. Now, there is something beautiful happened. What is that? Omega t minus px, not plus, minus. This dot product is Lorentz invariant. Why? Because the Minkowski metric, as you asked, right, is this guy, right? Eta mu nu diag. What I mean, the diagonal of eta mu nu is 1 minus 1 minus 1 minus 1. Particle physics people write it like this. Gravity people write it passive. Okay? So, I'm one of the gravity people, but Schwartz will write it like that, and if Schwartz did it, I have to. Okay? So, let me now come to the portion where we quantize. Okay? But before that, should we give a break? A break? A break? Okay. Let me now then continue. Okay? So where we left, we just try to expand this classical field, and we know that this, the immersion will give some kind of a plane wave propagation. I just classically solved it and write it in terms of plane waves. Okay? And now we will try to quantize them. Okay? We will try them, we will of course quantize them. So, what we will quantize, this is important. As you can remember, what we said in the Hamiltonian, we had position, we had momentum. We said that position now is position operator, momentum is now momentum operator. In field theoretical setting, if you remember, we have field phi, and we have its conjugate momentum pi, right, in the Hamiltonian. As I said, Hamiltonian includes degrees of freedoms. We try to quantize degrees of freedoms, physical degrees of freedoms, all of them, in a quantum system, in a consistent quantum system. So, we need to quantize this guy then. Okay? Now, it feels like this is the position operator. Okay? I just add the term operator, now I'm saved. Okay? Position operator is like, but now it's just field, scalar field, but it will correspond something like a position operator. Okay? Something like a position operator. So let's see. Okay, now let me just erase all of these guys. Okay, then let's assume that when we quantize the harmonic oscillator, right? This guy. Let me write it. Not with this pen, maybe. Maybe with this guy. Please, please, please. Okay. When we write it, right? We just try to quantize it, right? A dagger plus 1 over 2. This guy. When I write this, I said this is quantized. What I quantized was the modes. I quantized the system, and the energy eigenvalues I found are the modes, right? So, in the quantum field theory perspective, it have a name. Okay, it has a name. Okay, the name is the first quantization. Now we will do the second quantization, but please do not be confused that we are not quantizing it second time. It's just a name, semantics. Okay, it's just semantics. Please don't confuse it. It's that in quantum mechanics, we say in the quantum field theory perspective, we say first quantized theory is the quantum mechanics, and the second quantized theory is the quantum field theory. Okay, that's it. But it's just a name. We are not quantizing it second time. Okay? There's only one quantization. You are either quantizing it or not. Okay? That's it. If you can, be my guest. If you cannot, we're still trying to do the quantization for the gravity. Let's see. Okay. So, let me then write it. The first quantization, okay? First quantization is the discrete modes. Now we will do the second quantization. What we will quantize, okay, is just the number in the 1, 2, 3, 4, 5, number of, okay, each excitations of each mode. That means we will construct a Fock space. Okay, just heard the name, Fock space. Okay. So, 1. We have many quantum mechanical systems, all for each P. All for each P, we might have a quantum mechanical system. For each P, we have a quantum mechanical system. For each P, we have a quantum mechanical system. Okay? And the excitations of those, in that sense, will give the second quantization. Okay? All at the same time. Okay? All at the same time. So, in that sense, you will see, I will prove it, it's important I believe, we interpret, okay, and excitation as and particle. What I mean is this. You remember the Hamiltonian? I will write it in a continuous way. Not discrete, but I will take the continuum limit, let's say. Continuum limit. Omega p, AP, these guys, APs, right? AP dagger, AP plus 1 over 2. Like this. What I mean by omega p is the magnitude of the free momentum. Okay? So, now we will do something else. Okay? We will try to do something else. So, let's just, if we go to the continuum limit, that means we are not working with discrete modes, but we just take the integral, all of it, okay? If we do that, that means we're in the continuum limit. Now we cannot use the Kronecker deltas, but the Dirac deltas, right? You remember, in the quantum mechanics of the harmonic oscillator, we wrote this guy. And we said this is 1, are not committing. Ladder operators are not committing in that sense. In the continuum limit, let's say this is, okay? The AK, it's like P. I just use a different variable. AK, AP, P is the same with this guy, okay? Is now this garbage that I should carry with me because of this derivative in the Fourier transform, this division in the Fourier transform, okay? I have to carry this guy with me, and this. The three-dimensional, okay, momentum. What that means? In the continuum limit, when inside the integral, okay, this functional, when p is k, this will give me 1. That means that. Same thing. This is basically, if I say ij in here, this is ij, right? When I is j, this is 1. Same thing in the continuous limit, okay? Inside the integral, I have to define. Okay? Same thing. So, that means we can just act on the vacuum. What I mean by vacuum is the state that when you hit with the ladder down operator, it should give you 0 eigenvalue. Okay, 0. All 0. Let me strike that. That means this is a vacuum. Okay? If you hit with ladder down, it ladders down to 0. Nothing else. You have 0. Okay? If you try to ladder up this, right? It will give 1. In that sense, this one. Okay? N plus 1, n is 0, square root of n plus 1, 1, 1. Like this. Okay? But ladder down, that means if you have the vacuum state, you ladder down to find 0. That's good. That means you have a, let's say you have a stable vacuum or anything. Okay? So, then, now we can use this guy. Oh, I wrote it wrong. I'm sorry. There's a dagger in here. Ladder up. Okay? If you write this guy, oh, I'm sorry. Let me just write it like this. A dagger, okay? P to the vacuum. Vacuum, nothing in there, just vacuum. Okay. If I just try to do that, I will find this dude, okay? That means P, okay, is a state with a single particle, okay, single particle of momentum, what? P. That's it. Okay, single point momentum P. So you can find the normalization of all single particle states. Let's say you have to say the bracket of vacuum should be 1. That's the normalization. Let's say it's 1. Then, if you try to find the bracket of 2 different momentums, right? It's easy. You know that how we create them. You just try to pick them out. You know what is 0, 0. And you just find it. That's it, okay? Let's just do that. It will give you square root of 2 omega p, square root of 2 omega k, one from here, one from here, okay? 0, a p, a k dagger, 0. Why I write this? Because if you have this bracket, the ladder down operator, annihilation, will act as a creation to bra, and creation will act as a creation to cat. Okay? So this creates this side, this creates this side. Also, this annihilates this side, this annihilates this side. You can see in 2 different ways. Okay? But what I mean is, this acts on it, this acts on it, you can think of it. Okay? No problem. No problem. So, this will correspond to 2 square roots, it will come up as 2. Okay? 2, it's nice. And then square root of omega p, omega k. You know this guys, these 2 guys. Okay? And then we just build up the vacuums. So you can just find it like this. You remember this? Okay. Then this means 2 pi cubed, right? 3 p minus k in that sense, because this guy. You know this is AK, AP dagger minus AP, AK commutator relation, you know? Do you know the commutator? You know it, right? Okay. This is the commutator. It means AK minus AK multiplied with AP dagger minus AP dagger minus AK. Okay? It's the commutator. Okay. Then I can use the commutator and place it inside and write it a minus sign and just change the ordering. This is K and this is P, okay? And then acting like this. I just changed the ordering. What I said is basic. I said that this guy annihilates vacuum. Then this means if I act this to that, this will 0. I only have this guy, okay? Then, the result of this is square root of omega p, omega k, okay? 2 pi cubed, Dirac delta in the 3 dimensions, p minus k. Now I know what is the projection of 2 different momentums on top of each other. The result is this. That is, okay? So, in every consistent quantum mechanical system, you have to define all the operators in that sense, you have to produce them. One of them is the identity operator. Okay, you need to know what an identity is. You need to know what a 1 is. Right? 1 multiplied 2 is 2. Why? Because 1, in terms of multiplication, acts like an identity. Okay? So 0, in terms of addition, acts like an identity. 1 plus 0 is 1. It changes nothing. Under addition, 0. Okay? Same thing, I have to find the identity operator. I have to understand what is identity. Okay? That's really easy in that sense. Let me just raise this part maybe. So, let me define it. The identity operator, okay, is just this. In the continuum, of course, okay, I'm taking the integrals now because I have a distribution of points. I have to take the integral, right? If you had the mass, let's say, you have to take the 3-dimensional integral of the mass density, right? Mass density, so that you can find, I don't know, mass. Okay? Again, the same thing. You can think like that. I have to go to the continuum limit. So, let me just say, okay, these two. What I mean by this is this. If I have the K state, what I mean, the single particle state, that is momentum K. Okay? This means that. Okay? Is three-dimensional integral of momentum in terms of this guy 1 over 2 omega p. This is just bookkeeping. For every p I have this guy. Okay? And p, I'm just inserting it. You will see. Inserting it. Okay? You see, this k, if this guy is truly identity, when I insert this identity on top of this k, it should give me k again. This should be equal to k. Okay? This should be equal to k. Okay? So, I will, maybe I'm not going to do the maybe calculations, but I can just show it to you. It really is. Right? So, this fast calculation, okay? So, this will give that, you already find it. For every time p is k, it will give me 1. There is this dude. These will cancel. Right? These will cancel. Because, let's see. When p is k, this p is k. That means this vp squared comes out of the square root. This is top. These vp's are canceling. There is 2. 2's will cancel. And then, what I said when p is k, that means this p is now k, then we proved it. Okay? This is truly identity operator. Okay? So, now, by constructing all this, we can just directly state, okay, I now APs. These are truly ladders, creates. Then now, I will directly say that these are now quantum operators. Addition of the quantum operator will be a quantum operator. That means this is the quantum operator, the scalar field. So let me write in terms of the quantum field then. I'm just declaring it. You shouldn't have any problem with the declaring it, because when I'm declaring this, you didn't have any problem. Okay? Again, you don't have any problem. I presume. So let me just write it like that. Okay? Integral. It's now the quantum operator, okay? 3p cubed 1 over square root of. This is the homework for you. Please, if you can, do it. It's really important. Let me not say homework, but just something to study, something to understand, if you like. Okay? Something to understand if you like. Let me just replace p's with k. It's better it goes with my notes. And this is k. This guy again is k. This guy again is k. And this integral is on k. Okay? So, this is now, I'm declaring it, is the quantum operator. Then, the field itself is the quantum operator. I put it, okay? But what kind of a quantum operator is this? Because when I just say, okay, x acts on the position state, it gives me the position of the single particle at x. Eigenvalue equation. But what does this phi do? Let me just show it to you. Let me show it, okay? It does something remarkable. And let me just show it to you. It's the easiest way to see it, and I will show it to you. Okay? It's easier said than done, but again. Okay, now let's see. This phi depends on space-time. Okay? I will just write this guy. Phi operator acting on molecule. If it truly is what I said, then it should give me something beautiful. Okay? Let's check. So, this phi operator acts on the vacuum. Phi operator was this guy. Now it's an operator, so I write degree. Okay? So, let us act it with this guy. Let us act on it. Okay? So, first, I can do this. I can just took this P out and write it like this, right? 0 A P. It's my choice to make. Because what I said, the annihilation creates particles in bra and annihilates particles in cat. Okay? The other side. It acts on it as a creation. Okay? The P momentum, I just pick it out. And now I know the expansion of this guy. I just place it inside. Okay? Just place it inside. So, of course, there is a square root of omega p, comes from definition now. And then, this guy, d cube k, 2 pi, cube 1 over square root of 2 omega k, a k, e to the I k dot x, let me write it like this, plus a k dagger, okay, e to the minus I k x. Let me just write it like this, okay? And then, of course, it acts on vacuum. The question is this. Let me just ask it to you, just think on it. If this guy is Lorentz invariant, we just said that we have to work on a special relativistic setting. That means we have to keep on with the Lorentz invariance, at least for the observables, right? But this three-dimensional volume, what it means, if momentum truly is a Lorentz invariant factor, you just saying that by just writing this momentum, you say that, okay, in this space-time or in the momentum space, I pick up a volume. That means you are working with an observer. If you're depending on an observer, that means you are not working in a special relativistic invariant setting. So what the hell with this three-dimensional integral? This works, guys. This works in the sense that this is classical, but this, with this guy, this setting, all of this is equivalent, beautifully, equivalent to four-dimensional integral. Okay? This is basically a four-dimensional integral. Okay? Just let me give it to you the hint. I know that you all know how to take an integral. Just take an integral and show it. Okay? Just take an integral and show it. This is that. What you need to show is this. Here, okay? From minus infinity to plus infinity, dk, okay? This guy, this is Dirac delta, okay? And Heaviside step, k0, the zeroth portion, the first thing, k mu is equals to k0, ki, right? k0 Heaviside is equivalent to 1 over 2 omega k, okay? So if you try to write this in terms of that, you will see this will correspond the four-dimensional Lorentz invariant integral, okay? Just try to show, just pick it up, write this Dirac delta in terms of something else, and then put inside the integral, you will find that this is basically, this portion is Lorentz invariant. Even though it seems like not, it is, okay? It is. It is one of the beautiful outcomes of these Dirac deltas and the Heaviside step functions, okay? So, just try to do this, okay? But I'm not going to because I just need to hint on you, on it, of course. So, let me show it to you. Let me show it to you. So, you see, AP, AK, X on vacuum, this annihilates the vacuum, this portion is zero, okay? AK dagger ladders up or creates out of vacuum, so this portion is not zero. But I know how AK dagger and AP commutes with each other, then I can directly write this, right? Okay. Let me just come to the last part, okay? Not do all the calculations, but the last one at least. When you do all the calculations, okay, when you do this commutation and make it equal to zero, this side, this portion, and this portion with the commutation, you will find this. Why? Because there's 2 omega p, 2 omega k, and this comes up, okay? 2 pi cube coming from this commutator. You remember the commutator? 2 pi cube, okay? And then the Dirac delta, again coming from the commutator. Okay, nice. And of course, this guy, minus ek. Well, I mean, my k is momentum, okay? Okay, then, with this integral, 3-dimensional k, when k is p, this is k, this is p, and the integral can be solved. When k is p, these are cancelled, 2 pi's are cancelled, and this is just that. E to the minus I p dot x. Only it. The result is that. This result. So when the scalar field, quantum scalar field, acts on vacuum, okay, and contracted with p at a momentum at p, it will give us e to the minus epx. What is this? This is something really well known, okay? We found that the scalar field acting on vacuum contracted with P is the same thing. We found that this is the same thing as P x equal to e to the minus I p dot x. So this is the same thing by acting on vacuum. We find the same thing that the position state projected on the momentum state for single particle quantum mechanics. That means out of vacuum, the scalar field creates a particle at a point. So nothing in there. The scalar field excites the vacuum quantum field in a second, like this. There's this quantum vacuum. When I act with phi, phi just excites the vacuum, okay? And show me something like a position. Show me on that excitation, when I look up with my humanized body, I see an effective notion of a particle. So, field created a particle at a point x on that field by using the quantum field theory construction. That means that quantum field theory, in that sense, is the building blocks of the universe. When you have a quantum field, you act on it, you create a particle at a point. Act again, you create a second particle at a point. That's why I said in the second quantization, we are exciting every nth mode. We are exciting every nth mode. That means we are just creating a particle at a point. That's why phi pi in that sense is these guys are just creation operators. Okay? It created a particle at a point. That's why we are just saying that quantum field theory is the building block of the universe. Particles are just what we see effectively. Particles are just excitations of those fields. The maximum excitation, if you try to find the amplitude will be seen as a particle. That's a good thing. At least for the perspective of the flat quantum field theory, flat spacetime. But in the curved spacetime, I will explain maybe next week if you allow me, in that sense. In the curved spacetime, the notion of the particle is now broken. What is a vacuum? What is a particle? What is not a particle? Are just ambiguous. We have to pick the vacuum, in a sense. We have to pick which set of creation operators we will work on that curved background, so that we can create a particle at a moment at a position for the vacuum, but we won't even sure what the vacuum is. Because the flat spacetime, you see, okay? You have a position, you know that the position in here is good. You can write a Hamiltonian, you can write a Lagrangian, or let's say you can write a Hamiltonian, and that Hamiltonian will correspond to whole space. But for a curved spacetime, okay, let's say, you don't know. If you have a point, you can define, at a point you can define, at a point in time you can define, but next to it there is a curvedness, so you cannot. In the neighborhood of this, you can define a Hamiltonian, an energy function, and you can minimize the energy function to find the vacuum, corresponding vacuum. But in the curved spacetime, we don't know what is next when you come to the other side, because it's curved, not flat. That's why we have to be careful about what is vacuum, what is not vacuum. We have to look at minimization. We will just check the easiest way next week, okay? I'm not going to show how to quantize the how we just find the Hamiltonian. Maybe next week I can show it. We can just finish it now, okay? But let me just give you the hint. Next time, when we try to create a particle at a point, we will have a lot of problems, because this spacetime will be curved, especially Friedman universe we will use. It's the easiest one. Okay, it's the expanding universe. It's a cosmological metric. It says that we have the time and the expansion parameter. Okay, this metric is now that. Let me just write it on top of my notes. The metric will become this. This A is the acceleration now. Okay. Metric is now this. This acceleration is explicit time dependent. And when we said that Hamiltonian, let me write here, Hamiltonian is equal to energy, we just assume that we don't have any explicit time dependence. Frequency was time independent. We quantized it then. But now we have an explicit time dependence that is expansion of the universe. When the universe is expanding, frequency will be changed. Changing energy will give some observer like they are seeing a particle in there. But other observer will see a vacuum. Okay? So what is a vacuum and what is a particle will be ambiguous with respect to this metric when we come to that quantum field theory in the curved spacetime. Okay? Quantum field theory in the flat spacetime, especially with scalar field, all is good. We have a stable vacuum, static vacuum, operators evolved nicely, we just quantize it. But when it comes to curved one, it gets a little bit harder. Okay? So this is what we're going to do. Let me just show it to you. Maybe I can show it to you next week. Maybe we can do that next week. But in the sense that you see, we use harmonic oscillators. Okay? We use harmonic oscillators in that sense. You will see next week, because what we will do next week, I will start from here. I will go to the non-relativistic limit, and I will pick up the Schrödinger equation from here. Okay? And you will see, oh, we were just doing the Schrödinger equation, nothing more, in a relativistic setting. Okay? Just that. You will see that first order approximation of these equations will give you the Schrödinger equation in non-relativistic limit. If you go further, you can find the classical equations also. Okay? In different approximations. We will find that next week. And we will show that the quantum field theory, okay, is just the quantum mechanics with an infinite number of harmonic oscillators at every momentum vector p. The model is built by, at every point we have infinite number of harmonic oscillators. Their excitations will give us particles and other things, okay? For all quantum field theory. The reason is, maybe you can check that too, we are just, when we do the quantum field theory, we are just closer to the Gaussian fixed point. Gaussian fixed points allows us to do the plane wave approximations at the infinities. So we can just build up the standard model and the quantum field theory from this perspective. So we start with the harmonic oscillator. We will go with the harmonic oscillator because it's the easiest model that we can predict something. Okay? And we will do the same thing in the curved space-time too. Same thing. Okay? Again harmonic oscillators, again quantization, again same fields, but the results will be different.